Levy, Scientific Director, Holcim, Innovation Center, Lyon, France. He will be chairing the session, and I invite him to the stage, please. Already done. Thank you, sir. As a co-chairman, we have Dr. Abhishek Rai, who happens to be head of Group Quality Control and Quality Assurance, as well as Research and Development. I invite Dr. Abhishek to the dais, please. To represent NCB, I take pleasure in inviting Mr. Brijesh Singh, Group Manager NCB, as NCB representative. I would like to hand over the session to our chairman to conduct the session, please.
Thank you so much. Good afternoon, everybody. Very happy to be with you for this special session on chemistry. As a scientific director of Holcim, chemistry is obviously at the heart of our research. And in fact, when you look at everywhere, chemistry is absolutely everywhere. Chemistry is in our world, but also in construction everywhere, and obviously in the cement and concrete domain. When we say chemistry, which chemistry are we talking about? There are many, many different chemistries. We need, obviously, inorganic or mineral chemistry. We need organic chemistry. Also, concrete is very special. It's one of the unique materials where you've got the link between inorganic and organic, and this creates a special science, if I may. Physicochemistry is also important. And even Professor Karen this morning was speaking about earth chemistry. And I think it's another chemistry which is linked to geology, but it's very, very interesting. Frankly speaking, I think that among all the scientific domains in which we are working with, in our domain, in our business, or in cement and concrete approaches, I think chemistry is the most important. It's the most important to understand the mechanism of actions of very complex phenomena, which are extremely important also to understand and to develop solutions for the decarbonization. And decarbonization, chemistry is absolutely key at all levels. You need chemistry from, high temperature chemistry for the clinker. Reactivity is based on chemistry. Physical chemistry then, when you're speaking about rheology and so on. Durability is based on chemistry. Even CCUS is also dealing with chemistry. So you've got chemistry in cement at all the steps, all the life of cement and concrete. With this, I'd like to introduce a friend. I'd like to ask Shashank Bishnoi, Professor Bishnoi, to come and to present us a beautiful and formidable keynote. Thank you, Shashank. You can applaud him.
Thank you, Christophe. Good afternoon, everyone. So I'll wait for my... Yeah. So I have to look there while I speak so I can get my picture on the camera. Good afternoon, everyone. There is a very long title that you will see. On the program, but I've shortened it, talking about transport properties of carbonated cement blends, carbonated blended cements. Now, first of all, what is carbonation? Carbonation is, of course, carbon dioxide getting into the concrete, reacting with the alkalis. This could be sodium hydroxide, potassium hydroxide, but it's mainly calcium hydroxide that buffers the entire system, maintains a high pH, but then there are other things that can get carbonated as well. For example, the last one over there is C3S getting carbonated. I'm going to talk to you about it a little bit more afterwards. Now, when carbonation happens, the microstructure of cement changes. So it's very important for us to understand why, what kind of changes are happening to the microstructure, what that does to carbonation, and what that essentially in the end, what that does to the corrosion of the steel. Because it's not carbonation that we are worried about. Carbonation is not the problem. The problem is the corrosion of the steel that happens after carbonation has happened, and we would like to make sure that this corrosion does not happen. We know that as we reduce the alkali content of the cement or the calcium content of the cement, or I could very well say the clinker content of the cement, the rate of carbonation is going to increase. You see on the y-axis the carbonation coefficient, that's the rate of carbonation, and on the x-axis you have the total alkali in the cement. As we go down to lower clinker contents, we will have to be more careful about carbonation. This is something that we cannot avoid, but then at the same time, we cannot avoid going down to lower clinker factors, because we know we have to achieve net zero one day or the other very soon. I hope we won't have to wait until 2070 to achieve that. But then even what the cement industry says is, even after you consider all of the clinker reduction that you can, you would still have to rely 36% on CCUS. CCUS is an expensive technology, is likely to be an expensive technology in the future, which could drive up the cost of clinker 3 to 4 times. That will have a negative effect on our development. We do not want to rely more on CCUS. We'll have to have CCUS, but then to reduce our dependence on CCUS, we'd have to have a lower clinker content in our cements, because sustainability is important. But then at the same time, if we are reducing our clinker content in the cement, we are increasing the risk of carbonation and increasing the risk of corrosion. Then we may put we may have problems of durability, and structural safety and durability are more important, even though sustainability is important. So let's see how we can balance the two, how we can achieve a good approach. Now, when we started working on this issue, when we were just starting the LC3 project around that time, since before that, I have been thinking of trying to model all of these deterioration processes in concrete, because modeling is what I really love to do. So I told one of my students, and I said, why don't you go and draw me a simple short graph of what carbonation is, how carbonation happens. She went away, did not come back. I kept calling her, she did not come back. She came back after some time and she gave me this very complicated graph. I'm only showing you half of the flow chart. I'm not even showing you the other half. It's a complex process. This is what I realized. I used to think this is something very simple. CO2 goes in, reacts, and that's it. That's what it is. And then we realized there are so many steps to carbonation. There's diffusion of carbon dioxide, there is the dissolution, there is the reaction, there's diffusion of lots of other things, including moisture, there is precipitation of carbonates, lots of things can happen. So the first thing that I did is I bought a very high-tech microscope, which gives me very nice, beautiful images. The one that you see on the right, on that side, you see the beautiful image of the cement microstructure on the right. That is from my very high-tech microscope that I have. I call it MS Word. This beautiful image tells us that there are cement particles. The lighter ones, the darker ones are the hydration products. The something in between is the calcium hydroxide. You have the blue water. Of course, water has to be blue, unlike the sky here. The water has to be blue, and the rest of the space, the white part, are the pores through which the carbon dioxide can go in. CO2 goes in through the pores because CO2 likes to fly. It doesn't like to swim. If you have a bottle of Coke and you open the bottle, the carbon dioxide escapes, which means carbon dioxide would not like to remain within water. It would like to escape. It goes through the air and goes inside the microstructure only through the unsaturated pores. While it is going in, did I skip a slide? While it is going in, the water that is inside the concrete gets evaporated and escapes through those same pores as well. And as all of this process happens, there is calcium carbonate that deposits, or other carbonates that deposit on the surface of the cement particles and all the hydrate particles. You see all of those black rings? That's the calcium carbonate, a pretty impermeable layer that deposits on the cement particles, even on calcium hydroxide. So not all the calcium hydroxide can dissolve. A lot of it is still there, but can't dissolve because it's covered by a layer of calcium carbonate. And now we have these pores where where no more calcium can dissolve, and there is calcium inside, so the calcium will try to move from inside to outside the concrete, so there's another diffusion cell that is set up. So it's a very complicated process, lots of transport, reactive transport happening, and this is something that we wanted to model and understand. But one thing that we understood is different cements behave in a different manner. If I try to take the data from OPC that we have for the last, I don't know, 200 years is what we say, and I try to extrapolate that to blended cements, I would not be able to do that, because when OPC carbonates, the solid volume increases, but when blended cements carbonate, the solid volume reduces. At the same time, OPC has a lot of clinker phases that are remaining. When clinker phases carbonate, you see here a clinker grain that has carbonated, and you see around it a layer of silica gel, and the calcium hydroxide has gone out. But the important thing is, when clinker carbonates, the volume of the carbonation products is more than double the volume of the reactants. It's almost as effective, or sometimes even more effective, than hydration in filling the pores. That means it can reduce the porosity. Here you see in an SEM image, EDX image, of what this looks like. You have all the calcium that goes outwards from the clinker grains. The silica remains there in the form of silica gel. The calcium is all going outwards, producing more calcium carbonate. And what that does is it deposits in the pores once again. So if you have an OPC, if you look at the picture, the very nice high-tech picture that I have on the right over there, it shows that you have extra calcium carbonate that is depositing, which means it is blocking the pores. No more carbon dioxide can go in. Carbonation becomes a self-limiting process. But if you have a reduction in the solid volume, the pore volume increases, and carbonation cannot become a self-limiting process unless you have enough clinker remaining. All right, so that's something that's very important. Now, when we talk about these blended cements, be it fly ash-based cement, PPC, or LC3 or composite cement, we know that the permeable porosity of these cements has a finer pore size. The resistivity of these cements, concretes made, we use these cements, is high. But after carbonation happens, these pores become coarser. This is something that we have to clearly understand. Pores become coarser in all blended cements because of the process that we've just talked about. Even though the total permeable porosity might reduce, even then, because of the change in the microstructure, you get more connected pores, and the carbon dioxide may be able to go in more easily, which means, and because the pores are better connected, compare the blue ones with the red ones show the carbonated ones, the water gets in more easily. The air gets in more easily into the concrete after carbonation. So we need to take care of that, which means that all of these blended cements before carbonation, that are the ones on the left, when they used to have lower transport properties before carbonation, after carbonation the transport properties can be higher than OPC. That means all of our experience of 200 years of OPC is a waste. We cannot extrapolate from that experience to design our structures using blended cements. Any of the blended cements, even PPC by the way. And because the corrosion rate is going to be higher as well in that case. Now, something very simple that we know about, all of us know about, but we don't practice it so well, is the control of water to cement ratio. Here what you see are 3 different water to cement ratios in the vertical graph. On the vertical side over there, 0.4, 0.5, 0.6. You have the different cements, if you wish, on the y-axis, and that way you see that if you reduce the water binder ratio, you would be able to reduce the depth of carbonation. That is something that is very important. That is something that is a simple way in which you can control the depth of carbonation in any blended cement, which is why when we amended IS 456 to include limestone calcined clay cement, and now I feel it should be there looking at the data also for composite cements, we have asked that the water to binder ratio be reduced by 0.05. I must tell you frankly that the current recommendations of water to binder ratio in IS 456 are good. The problem is that our current construction practices do not always meet those requirements. The standards we try to make on the safer side most of the times, which is why we are having to reduce this. If you just take the values that are given in the code and follow them religiously, you're not going to have these problems. But because we do not follow them religiously, we have to do things like this. But there are other ways of solving problem of potential corrosion or carbonation as well. Here we are showing you some results using different waterproofing compounds. Now, our idea was that if you have low clinker cements which get carbonated faster, if we can mix waterproofing compounds and prevent moisture from getting in, at least we can protect it against corrosion. That's what our idea was. But then after we mixed in these waterproofing compounds, we found that even the carbonation reduces. So with some of these waterproofing compounds, which are just, you cure the concrete, after it dries off a little bit, 10 days, 15 days, 1 month, whatever, you come with a brush or a roller, you just apply this compound on the surface. This could be a hydrophobic compound, for example. Just apply this on the surface of the concrete, carbonation depth reduces. And the carbonation depth reduces because even for carbonation, you need moisture. You have to have a layer of moisture around the cement particles for it to be able to dissolve and react with the carbon dioxide, and even that process is slowed down. And what you notice is not just the carbonation depth, but also because you're reducing the carbonation, you're also reducing all the other transport properties in the concrete, which means that by a simple application on the surface, we can get a concrete that is going to be durable in carbonation conditions. We can go down to those low clinker factors safely. But then a lot of this work has been done in the lab and not in the field. We wanted to see what's happening in the field. So we were very fortunate. We had an old building in the campus, 50 years old. We were going to demolish it. And so what we said was, I asked my student to stand inside the building when it was being demolished. No, not really. But I asked him to take samples from there, measured the carbonation depth. Most of the concrete was fully carbonated, at least beyond the reinforcement. And the funny thing was that the cement looked like calcined clay cement. Calcined clay was quite common. The sand also used in Delhi was quite common in that time. That was also quite commonly read at that time, but there was also calcined clay cement available at that time. And we look at the XRD graphs, we see that there is quite a bit of molite in there. I wanted to show you more results, but our Bruker XRD keeps broken down more than half of the year, so I could not show you more or better results today. I hope they can improve their services so we can get something better. But this shows that we have molite here, and to me, getting molite in cement, the easiest way of doing that is to have calcined clay mix in it. You've probably over-calcined some of that clay. So this is probably calcined clay cement that is in there. Despite all of the concrete being carbonated, only at 20% of the locations there was actually corrosion. So what Lupesh did was he took out samples, he measured half cell potential and rate of corrosion, but he actually also took out the reinforcement to see if it has actually corroded after 50 years of service in Delhi. Delhi has some of the worst climate, well, worst climate full stop, but worst climate for carbonation as well. So we also found that it all depends on the microclimate. We were able to identify which locations in a structure suffer the most from the risk of corrosion. We know this kind of graph already. I'm not going to spend time on that, but the microclimate is what is important. Now, I said that safety is important, durability is important. Yes, it's important. We need to find solutions to all of that. I think we have the solutions to those things, but there is one more thing that we really have to think about. Do we really, if we want to achieve sustainability, do we want to use the same type of cement everywhere? Do you wear the same clothes when you come to this meeting and when you go to sleep? No. Do you use the same kind of vehicle when you want to exercise and when you want to go transport yourself, or when you want to travel to America versus when you want to come to Yashobhumi? No, you don't. You use different products for the same industry for different things. Cement industry and the engineers have to become smarter in that way. On the left, there's a picture of Kedarnath. We had a project there, if you know about it, Adi Shankacharya Samadhi that was made over there, support of JSW Cement at that time, and JSW, not just JSW Cement, the whole group. And there, the requirement is freeze-thaw resistance. This next building in the middle, the horrible one, has been in the terrible weather in Delhi. The one on the right is a beautiful bridge that goes to these beautiful islands in Cuba, exposed to chlorides. Should we use the same cement everywhere? Even in the same house, should you use the same cement in your foundation as you're using in your drains? This is a question we have to ask, because if we have to get to sustainability and reduce the clinker content, we have to have solutions for specific applications, because we know that all of these blended cements that you see on the right, they're very good in some of the conditions, but can be worse in other conditions. For example, here, they're very good in chlorides. We should start using them in chloride conditions, for example. And be very clear, engineers are supposed to carry out construction. They're supposed to know what to use where. You're not going to put a beam where there's a column. I'm finished.
20 seconds.
20 minutes? Okay.
Seconds.
So, should we worry about carbonation? Yes, if the microclimate is right, but not in many cases. The accelerated tests may not represent the reality, but we should not hold the development of sustainable cements hostage to the fear of carbonation, and we should develop an industry that works on the industry. 20 seconds, that's up. Thank you.
Congratulations. It was, as usual, a fantastic presentation.
Thank you.
Even, maybe this one was even better.
Oh, really? Okay.
really impressive.
What
Thank you
can
so
I
much.
say? I matured well.
I think it was a very nice presentation, and as a keynote speaker, you have covered the carbonations, the impact, the porosity, what is the relations, and also with the blended cement, what can be the impact of carbonation, and how to get rid of using that. One thing that was very important, I have seen that to reduce the impact of carbonation through this waterproofing. So I want to understand in detail if you can, maybe after this session.
I have a guy called Love Singh sitting here. Love, raise your hand. Taller. So Love Singh is the guy who did all the work.
Yeah.
So hire him to...
So just one question, that if we want to reduce carbonations with the help of waterproofing chemicals, so like what is the reactivity happening and how you can avoid the carbonation with the help of this waterproofing chemical?
This is something, maybe it will take a longer discussion, but we could not understand it at first, but we've recently seen literature from Maruyama in Japan. And what they're showing is that you have to have the right relative humidity even for carbonation. So if you're able to subdue the relative humidity, you can even reduce carbonation in concrete. And the pH remains high. Okay. So this is something, maybe this is related to that, but we were very surprised at the results.
You are avoiding the moisture.
We wanted to avoid the moisture,
yeah,
but we were able to reduce the carbonation as well. This was unexpected.
Okay, great, thanks.
Yeah. Thank you.
Applause again, thank you so much. Now I would like to call the people Shiv Sai Trivedi, Bibhuti Duzandas or Salim Barbhuiya to speak about the phase quantification on CO2 uptake in sustainable binders subjected to accelerated carbonation. Thank you, sir. You've got 7 minutes and 0 seconds. Okay. Thank you so much.
So a very good afternoon to one and all. I am Shiv Sai Trivedi, a full-time research scholar from the Department of Civil Engineering at National Institute of Technology, Karnataka, Surathkal. And currently I am working under the guidance of Professor Das, who is also a professor in that same department. Okay. So the contents are as follows: the introduction, followed by the objectives, materials used, experimental work, and results and discussion, followed by the conclusions. Okay. So the supplementary cementitious material, as we all know that the SCMs are used as a partial replacement to OPC. Why? In order to improve the engineering performances as well as to provide us a sustainable solution that the cement industry has been looking. Since this cement industry is also known for emitting around 8 to 9% of the global greenhouse gases emissions as well. So making use of the SCMs become extremely important in this regard. Also, it has been seen that there are certain SCMs such as fly ash, granulated slag, silica fume, metakaolin, and these kind of certain emerging as well as future SCMs are going to be extremely important if we are going to incorporate them in further for the development of the cementitious composites. As shown in the ternary diagram here, there are a range of emerging as well as future SCMs, and SCMs provide us a greater amount of strength, packing density, microstructure, and durability. So the accelerated carbonation treatment, today we are talking about achieving India's goal for net zero by 2070, and there are certain technologies such as carbon capture, utilization and storage. But the question is, do we know the individual CO2 uptake capacity of these SCMs? Because at the end of the day, we are going to use these SCMs for the development of the cement and concrete composites. So with this objective, this accelerated carbonation treatment become extremely important. And also further, in this accelerated carbonation treatment, we will see the accelerated controlled version of this natural occurring phenomena, where under a gaseous CO2 system, there will be a microstructural refinement, and that will take place within few minutes to few hours. As per the reaction kinetics in the accelerated carbonation, here this CO2 will react with the water, will form the carbonic acid, and this carbonic acid will further react with the Portlandite, and this will form the CaCO3 or calcite. Now what this calcite will do, this will occupy the pore structure in the matrix and will further densify the microstructure. And well, this is a complex process here, and from diffusion to precipitation here in the form of various precipitates, this will further densify the microstructure. With the aim of the carbon capture, utilization and storage of these carbonated binders, this study comes with the objectives in order to study the phase development in the finer to ultra-finer SCMs subjected to accelerated carbonation, to study the microstructure characteristics of carbonated and non-carbonated SCMs, also to determine the individual CO2 uptake capacity of these sustainable binders that we are going to incorporate further in the cementitious composites. The experimental design is as follows. The SCMs were selected and procured, followed by the prelim investigation, and this carbonation treatment and the sample collection, followed by performing certain advanced characterization studies. Here in this study, we have taken fly ash, ultrafine fly ash, granulated blast furnace slag, and alkofine, the finer version of GGBS, followed by its accelerated carbonation treatment, and performing certain microstructure analysis and doing the phase quantification. The material used are here are following the Indian standards from OPC to alkofines. The experimental work is as follows. Here the carbonation curing regime is followed by certain standard references and performing the advanced characterization studies using scanning electron microscopy, energy dispersive X-ray spectroscopy, Fourier transform, infrared spectroscopy, and thermogravimetric differential thermal analysis. The results and discussions are as follows. These are the SEM images from A to J. These are certain carbonated and non-carbonated SCMs. And here we can observe that in case of non-carbonated samples, there is an irregular and non-uniform surface with certain voids are being observed. Whereas for the carbonated samples, the presence of taubermorite or CSH as well as CaCO3 is predominant. Again, the energy dispersive X-ray spectroscopy here, we have tried to calculate the Ca by Si atomic ratio. And for the carbonated samples, it has been observed that these values are fewer than 2, representing a denser microstructure. These are the FTIR studies of the carbonated and non-carbonated SCMs. And here it can be observed that certain phases such as calcite, vaterite, polymorphs are being observed at these shown wave numbers. And due to the larger areas of the carbonated samples from the non-carbonated SCMs, this further represents a densified microstructure. Now the TG analysis. Here it can be found that there is, in case of the carbonated GGBS, this dark blue TG is this graph. So here it can be observed that there is a huge mass loss, particularly for the carbonated GGBS. And this has resulted to enhanced CO2 uptake and formation of calcite fractions. Here we have calculated, and this, in case of carbonated GGBS, we have obtained till 16 to 17% of the CO2 uptake. Now the conclusions, following all these microstructure analysis, it has been observed that the CSH was actually consumed during the accelerated carbonation, and then it was converted to these calcite phases, be it calcite, vaterite, aragonite, and all these phases, and that densified the microstructure also. It has been discovered that the carbonated GGBS exhibited the highest proportion of CaCO3 that resulted in an enhanced CO2 uptake of the developed composite. Thank you.
Thank you so much, and congratulations for the timing and also the quality of presentation. We will have questions at the end of the papers. Okay? Thank you.
Thank you. Thank you, everyone.
Now I'd like to call Himanshu Guleria, Harveer Singh, and Dr. Shweta Goyal, one of them from TARPA Institute, to speak about investigation on GGBFS-derived mix by using CCUs based on accelerated carbonation curing. You've got 7 minutes and 0 seconds. Thank you.
Very good afternoon to all. Myself, Himanshu Guleria. I'm here to present the presentation on the topic investigation on GGBFS-Derived mix by using CCUS-based accelerated carbonation curing. Okay, so my presentation, the content of my presentation, introduction, then I will be talking about the accelerated carbonation curing process, reaction mechanism, methodology and the laboratory process, followed by the materials used and mix design, and then results and conclusion. So as we know, the CO2 emission has been on increasing trend with the rapid urbanization. As we can see, the world, currently the world contributes, if we talk about the cement industry only, the world contributes about 38 billion ton, whereas in India, the cement industry contribute 177 million ton, which approximately about 6%. If we consider the construction sector along with the cement industry, the total CO2 emission is in the overall contribution is 40%. So in light of some targets in the various forums like COP21, Race to Zero campaign, COP26, we need to minimize the CO2 emission. So we need to have some mitigation techniques. If we don't use the mitigation techniques and we follow the same trend, by 2050 we will be having 2.34 gigatons of CO2 emission, and with mitigation technique we can limit it to 1.5 gigatons. So what are the mitigation techniques? Okay, so there are some mitigation techniques like alternate fuels and raw materials, improve efficiency of cement rotary kilns, supplementary cementitious material, and carbon capture and utilization. So among these, CCUS has been identified as one of the major efficient mitigation technique which can reduce the CO2 emission. CCUS in concrete we can use in three methods, either by in recycled concrete aggregate, batching and mixing, and early age carbonation curing. So I will be talking about accelerated carbonation curing, which is also your early age curing. So accelerated carbonation curing has been identified as a curing process for a precast material in which CO2 is basically exposed to concrete, freshly prepared concrete. By using the accelerated carbonation curing procedure, we can also reduce the uses of water, as we don't have to use it in the water curing as well. So what is the reaction, how it is different from the water curing and the CO2 curing? In water curing, the major products are CHS gel and calcium hydroxide, whereas in the CO2 curing, the unhydrated compounds and hydrated compounds, when reacts with CO2, it gives us CHS gel and calcium carbonate. Also, one of the objective of using the SCM is to efficient use of SCM will diminish the carbon emission associated with the Portland cement. Another, to minimize the environmental effects such as waste by efficient utilization of industrial solid waste. The methodology adopted in this, the specimen were casted, two types of curing were given, carbonation curing and the water curing. Some basic tests were done like compressive strength, water absorption, sorptivity, acid test, rapid chloride penetration, and microstructure like mineralogy and morphology. In carbonation curing, the laboratory process which was followed in 4 steps. First step was in mold curing, then preconditioning, followed by the carbonation curing for 12 hours, and then post-conditioning. In post-conditioning, 3 days of water curing was given, and then followed it with the sealed plastic belt till the testing gauge. So the material used, these are the basic chemical composition and physical properties of the OPC43 and GGBS used in this study. For the mix design, there are 4 types of mix designs were used. The GGBS basically replaced by weight of the cement as 20%, 40%, and 60%. So in results, for the compressive strength, the green one is showing for the carbonation curing, the blue one is showing for the water curing. At all the mixes, the carbonation curing showed the better results compared to the water curing. In 28-day, the results were almost similar, but still the carbonation curing showed the better results. Similarly, in the water absorption decreased as compared to water curing, and the 40% GGBS mix showed the optimum value as compared to the 20% and 60%. For the softivity results, the softivity decreased with the increase in the GGBS content. In the RCPT test, which is rapid chloride penetration test, the carbonated samples showed the lower chloride permeability at all the ages. In acid test, the percentage loss was in carbonated sample compared to water curing was lower. The 40% showed the better results. In the XRD results, in the microstructure, we have done the testing on the 40% GGBS mix. It shows the calcite peaks in the carbonated cured samples as compared to water cured sample. Whereas in the morphological testing, in the water cured sample, calcium hydroxide was observed, whereas in the calcium carbonate samples, it was a denser microstructure was observed. Conclusion, the highest strength was found in the 40% replacement. Therefore, it can be said that 40% was the optimum replacement level of the GGBS in the concrete. Water absorption of carbonation cured sample was lower than the water cured samples at all the ages. Chloride permeability of carbonation cured samples was significantly lower than the water cured samples. And in the microstructure, the calcium hydroxide phase was reduced significantly, while there was considerable increase in the calcium carbonate phase as indicated in the XRD test, and the denser microstructure was observed in the SAM images of the carbonated cured samples. Thank you.
Thank you so much. Question will be raised at the end. Thank you. Appreciate. Now I'd like to invite Koluru, please. I know everybody call you KV, LS, but it's too complex for me. I prefer to call you by your first name. To speak about reactive potential assessment for efficient utilization of fly ash in alkali-activated uncementitious binder. Thank you, and the floor is yours. And you've got 7 minutes and 10 seconds because you're my friend.
Okay, thank you. Thanks, Christophe. So let me get started right away. What I'll be presenting about is the utilization of fly ash effectively. That is, we're talking about countries that do produce a lot of fly ash. At least in India, our production is only going to increase. We're not cutting back on the consumption of coal for producing power. It's the best way to produce power. And so we're going to produce a lot of fly ash because of that. Now the question is, even the one that we have, are we using it effectively? Which means we need to understand what fly ash brings to the table. Now, if you look at fly ash under the microscope, you see all these beautiful phases in there. These are actual micrographs that we took in our lab, but the business end of it lies in these spheres that are the glassy spheres that basically contain the reactive material. Now, what we did is we collected fly ash from different sources across India, did the oxide analysis. The oxide analysis reveals that the composition is primarily similar. If you just go purely by the oxide composition, it's going to be very similar across the different fly ashes. You can't pick out the differences. Typically, our fly ashes contain very low calcium. This has consequence, as I'll explain a little later. But then you can actually determine from the known stoichiometry, you can actually determine the crystalline phases like malite and quartz, in which silica and alumina are present in crystalline form, which is predominantly in a non-reactive form. They have known stoichiometry, so you can subtract out the amount of silica and alumina that is present in those forms, and actually determine the reactive oxides that are present in the glassy phase of fly ash. And if you look at it, now the story changes. So what you see here is the total reactive silica. The blue bar shows the total silica, the green bars will show you the reactive silica. So this is the silica that is present in the glassy form, the cenospheres, the plerospheres. And on the right hand side, your right hand side, you see the other graph, which shows the blue graph shows the total alumina that you get from an XRF analysis. The green bars will show you the reactive alumina that is present in the fly ash. Now, the reactive part is what we are interested in. That is what basically we can count on if you're going to do any kind of replacement reaction. The other thing is if you're going to do alkali activation, it's the alumina that plays the key role, particularly when we're talking about geopolymers. Now, the other thing is if you look at classes, you can actually synthesize classes, and as the ternary diagram here shows, you can have glasses that basically, if you look at the CASI and AL, phase diagram, the glasses that we find, or the glass form that we find in our fly ash is mostly the glass C that you see. It's very low in calcium, and the silica and alumina more or less balanced, the proportion if you look at it. And this is actually a non-reactive glass, whereas if you come towards the calcium end of this ternary diagram, you can start getting reactive glasses. This is what you would see in slag. So that is the glassy form that's present there is actually quite reactive, and you don't need to put effort to extract the reactive species from that glass. Now, when you subject it to alkaline dissolution, this is what we've done here, is to basically put it in an alkaline solution, leach out the silica and the alumina from there, and you see that there's a, if you see the graph on the right hand side, there's a steady decrease of silica and alumina that comes out from the glassy phase of fly ash, and you can actually completely deplete it. The interesting thing is that if you look at the XRD spectrum there, the peaks are all the crystalline forms. These are primarily inert. Those don't change with the dissolution of the glassy phase. What changes is the hump. You see a hump that's formed in the XRD spectrum on the left-hand side between 20 and 30 degrees that you see. That hump slowly disappears. The crystalline phases are more or less inert. They do not participate in the reactive, in any other reactions. So, coming to aluminosilicate binders with fly ash, what do? We dissolve the reactive silica and alumina into the solution. Then basically we form geopolymers, which are basically cross-linked silica alumina chains that are formed in the system. So, one thing we found with the dissolution of the glass is if you look at the XRD analysis of the dissolving glass, the characteristic of the glass itself doesn't change. The XRD signature of the glass with the dissolution does not change, and that's something we've established. So you could actually continue to use XRD to quantify the glass in a partially dissolved case of fly ash. Now, this is the key slide that we basically came up with, is to use the fly ash in a very effective manner, particularly for producing geopolymers. Fly ash, if you look at the two arrows that are coming out of there, contributes reactive silica and reactive alumina to the system. To this, you typically use activators, which are sitting on the box at the top. You use water glass or sodium silicate, sodium hydroxide, and water. Now, sodium silicate contributes silica and sodium to the system. Sodium hydroxide contributes sodium to the system. And then, of course, you have water that balances the pH of the system. Now, what you get in the system, in a geopolymeric system, is much more complex than what you see in a cement paste, because in cement paste, you only deal with water to cement ratio. What you have here are the reactive ratios. You have silica to sodium ratio, alumina to sodium ratio, in addition to the molarity of sodium hydroxide. So you have to play with all of these three things to figure out what is the optimal of these ratios, which are based on the reactive content that is coming from the fly ash. If you do that, what we found is that the reactive silica to sodium ratio, and these lines that you see are for different reactive silica to sodium ratios, varying from 6.55 to 2.66. The 2.66 is on the top, the 6.55 is the line at the bottom. These were the geopolymerization was performed for using sodium hydroxide solutions of different molarity. What you find is if you actually increase the molarity beyond 3 molar of sodium hydroxide, it really doesn't make any significant improvement. So you really don't need a very high molarity solution like what people have used in the literature. You don't need 14 and 15 molar sodium hydroxide. You can manage with 3 molar. And the optimum ratio of reactive silica to sodium in the system is anywhere between 4.72 and 2.66. So that is basically the optimal ratio. That will give you the best case strength from the system, where you use up all the reactive material in the fly ash. Just the last slide. So what determines the strength in the geopolymer system is the alumina that comes from the fly ash. And so we selected 2 fly ashes with very different reactive alumina in them. And you see that the strengths that we get, even using the optimal ratios with the activators, are night and day. The one which had the higher alumina content gave us the much higher strength. The one with the lower alumina content gave us much lower strength. So with this now, we can come up with a, this is stuck. Yeah, so we can actually formulate idealized mixtures which are based on the composition of the fly ash, where the fly ash is used effectively utilizing all the reactive species in the material. So with that, I'd like to thank you for your attention, and I know Christophe can't wait to chase me off off the stage.
That's perfect. Thank you so much, Gulu. Really appreciate it. That's fantastic. Next will be Rashesh Kumar, Shashank Bishnoi again, and Gopalakrishnan, speaking about synthesis and characterization of high volume M3 halide polymorph. The good news is not you, Shashank. Thank you.
So, good afternoon, everyone. Respected chair, co-chair, NCB representative, and all the dignitaries of the dais. So, this is the part of my ongoing PhD work under the guidance of Professor Shashank Bishnoi and Gopalakrishnan sir. And the topic of this presentation is about the synthesis and characterization of high volume monoclinic halide polymorph, which is the prerequisites raw materials we have synthesized in our laboratory in high volume for the work which is regarding the influence of curing temperature on the hydration and macrostructural development of pure cementitious phases after addition of different mineral and chemical admixtures such as calcine clay and alkali contents by varying the alkali contents. So the content of this presentation would be, firstly I will cover briefly about the introduction materials method, in which I will discuss about the selection of raw materials, the purity, the particle size distribution, the synthesis protocol that we have optimized, the factor influencing purity, and the phase formation role of stabilizer. We have taken few stabilizers to stabilize the monoclinic form of that halide. The results in which we have developed more than 95% pure M3 polymorph of halide along with the physical properties, and although we have done FTIR, SAM and XRF and other studies, but I will cover here only the XRD analysis, followed by the comparison to traditional method, and regarding the efficacy, efficiency and scalability, and followed by conclusion. So as an introduction, this is very basic that halide is the major phase which covers about 50 to 70% of cementitious mass, and it is found in 7 form, that is T1 to T3, M1 to M3 and rhombohedral. And the crystals chemistry and polymorphs depends on the dopants which is being used during the sintering process at higher curing temperature, and according to the binary phase diagram which I will discuss later, the formation of halide is generally takes place the temperature more than 1250 degrees centigrade. So in the past, different dopants have been used on the such as magnesia based, alumina based and iron based, which plays a role in stabilizing specific polymorphs. Therefore, this study addressed the challenges that we have faced for stabilization of M3 polymorphs of halide for mass for production up to 4 to 5 kg of this polymorph M3 halide phase. So this I was discussing earlier, that the formation of different polymorphs such as halide or belite depends on the phase diagram, in which as we move towards the right, the formation of the calcium to silica ratio will decrease, and the formation of C2S or CS based polymorphs will form. So our concern was towards the left side, as the formation of C3S, the M3 phase was our target, and that target was achieved by addition of MgO and the addition of Al2O3. So this study seeks to the development of the synthesis of M3 halide using the solid state sintering process, which was done up to 7 hours, and we have developed about 1 kg of that M3 phase of halide within 7 hours, with the sintering time up to 7 hours, with dwell time of 4 hours, and the ramp rate of about 8 degrees centigrade per minute. So as raw materials, we have taken the pure raw materials, that is limestone, So this was objective, as I had discussed earlier. So as raw material, we have taken the pure limestone with purity more than 98% and silica fume with purity 99%, which was the key factor, because if the purity is less and the pure analytical grade of these two material is doped with, you say P2O5 or something else, so the formation of beta phase, that C2S phase will occur. So we have taken highly pure these two raw materials along with the MgO and Al2O3 base stabilizer and material preparation. The particle size distribution of limestone, the D50 size was about 3.27 micron, but the particle size distribution, based on the particle size distribution, the D50 size of silica fume was about 134.5 nanometer. So, so we have done the trials on the basis by taking the same particle size distribution, but the formation of halite was not obtained, and the more amount of free calcium oxide was occurred, and which increased the lime saturation factor, of course. So we have reduced down by milling in ball mill at the rate of 70 RPM for 30 minutes, and by doing so, the particle size distribution, the D50 size was reduced from 135 to about 3.27 nanometer. And then we again did the solid state sintering process after homogenization. And we have also taken the two process. One is compaction and with compaction and without compaction for effective grain diffusion for formation of the pure phases. So this is the sintering condition. More than about 70 trial mixes we have synthesized. I am showing here only 4 due to time constraint. So ranging from 1450 to 1650 based on the binary diagram which I showed earlier, and the dwell time was ranged from 2 to 6 hours for optimal conditions. So the mix designation was A1, A2, A3 and A4, and the compaction with and without compaction technique were used, and resistance time was 3 and 4 hours for these mixes. In few mixes we have added stabilizer, that is MgO and Al2O3 based, and cooling was that is slow cooling and rapid cooling with the optimum rate. So these are the analysis technique which we have used. 1.2% by weight of MgO and 1.01% Al2O3 was used as stabilizer. This is the molar equivalent which we have used, and for the cooling, rapid cooling was at the rate of 180 degrees centigrade per minute, which was the optimized conditions. After the sintering and synthesis of the halite phase, we have put into the silica gel after grinding for further analysis. So directly, sir, I will come on the XRD analysis due to time constraint. So what we have observed that for A1 mix, in which no compaction was there and the stabilizer was added. So we have seen that in the rapid cooling, because the stabilizer was not there, the triclinic phase was observed. But when we have added the stabilizer in A2 mix, and when the compaction was done, and we have seen, sir, only 1 minute, sir. Yes.
10 seconds.
Okay, okay, sir. Okay, sir. And the final optimized mix was A4 mix with the purity more than 95%. And this technique that we have taken was far better as compared to the other technique which is available in the literature in terms of time, efficacy and resource efficiency. So these are, sir, conclusions. The final conclusion was that we can develop about, in one run, about 1 kg of pure halite phase in monoclinic polymorph within 7 hours. So this was the final conclusion. Thank you.
Thank you so much. Now, I'd like to invite Usha Sharma to speak about the impact of silica nanoparticles on silicate structure of calcium silicate hydrate gel during early age of hydration. Thank you.
Very good afternoon, one and all presented here. I'm going to present the early age cement chemistry, basically, in the presence of silica nanoparticle. and the concrete, which is one of the most widely used man-made material at this time, but it has a huge carbon potential, carbon footprint due to of its key ingredient, which is known as Portland cement. Now, what is the challenges with the Portland cement is the cement hydration and its challenges. What is the basic challenge of the Portland cement? That it's hydration chemistry. Actually, what happened when the Portland cement react with the water, it's form another complicated materials which having lot of different compounds and porosity, which need to understand basically this magical materials transform into the solid within a 1 day or 28 day, and after the years it leaches out. Leaching property is the major concern which reduces the service life of a concrete, and that is the basic challenge which can be understand or which can be regulate by understanding this early age hydration chemistry, which is very complicated but very important to address because it has multi-steps, and these multi-steps has different chemistry. So we need to focus, we need to understand that how the chemistry is changing during this time period. And the second one is microstructural modification occurring at this stage. The product, calcium silicate hydrate, which is basically known as the DNA of concrete. So no one knows the stoichiometry of this CSH, and if we can identify that what is the stoichiometry of this CSH and what type of CSH is forming at this time, we can manipulate or we can change the service life of concrete. So this can be one of the strategy which can reduce the environmental footprint by increasing the service life of concrete by optimizing the molecular level changes in calcium silicate hydrate. Now, there are many additives which is being used in the concrete to increase the performance, and one is silica nanoparticle, and because it has lots of special properties, it is widely used and accepted as well. Today I'm going to discuss that how basically the chemistry is changing during this time period. This is this complicated graph of first 24 hour, and the moment here I will talk about basically the C3S reactions in this phase, that when the cement react with the water, these ions dissolved, and we got these intermediate phases within this time frame, and we can see that the heat of hydration is get reduced down, and the dormant period basically get started at this time moment. When these intermediate product converted into the final product, our acceleration period basically started. Now, the point is very important to understand that this conversion, the type of CSH which is forming, which is known as intermediate CSH, which is also known as CSH type first and converted into the CSH type second, the stoichiometry is changing with this time frame is very important to understand, and then only we can bring the innovatory changes into the cement industry. With the silica nanoparticle, how the basically reaction changes, that in presence of nanosilica, we got this additional hydrated silicates ions, which forms CSS seeds during very initial early age of the hydration, and which gives additional nucleation effect. Nanosilica itself gives the nucleation effect, that's why dissolution rate increases, but the moment CSS seeds are formed, and these CSH seeds accelerate the reactions during the acceleration periods. And that's why the dormant periods get reduced, and we see the reaction kinetics basically accelerate during this time frame. This additional CSH, which is forming at this time period, how it is changing we know that the hydration reaction accelerated. We quantify and we have find out that due to the formation of these additional CSS, within 8 hours, acceleration is observed with the formation of additional CSH as well as CH. Both the products are higher, so showing the additional acceleration. But at 24 hours, we find out the CH content is significantly lower than the control, while the CSH content is higher. So this is called nucleation reaction at the 8 hour, and we mention it as a pozzolanic reaction. We can say so that it is a pozzolanic reaction. It means nanosilica is regularly consuming the CH over there. Now, what is basically how it is affecting the further scenario and how it is changing the structure. This has been done with the FTI analysis, and we have just monitored the first 24 hours. And we have seen that in case of the control, the change into the spectrum is showing that the system is quite amorphous. But with the nanosilica, we have got a more order structure because Q1, Q2, Q3 peaks were there. We have done the deconvolution of this FTIR data and quantify the Q0, Q1, Q2, and Q3 peaks, which shows that with the nanosilica, we have additional Q3 peak, which is not present in the control system. Further, the NMR analysis has been done, and it was observed that Q1, Q2, and Q3 peaks are observed with the silicon nanoparticles. And when deconvolution analysis is done, it is observed that heat of hydration is increasing as well as mean chain length of CSH is also increasing. That's showing that how it is changing the microstructure within first 24 hours. Further, nano-indentation technique was done to understand the packing density, and this shows that when we incorporating the nanosilica, the HD CSS quantity is increasing. That's showing that the packing density basically increases. So finally, I would like to conclude in this that the first 24-hour chemistry is very crucial, and it is very important to understand with using the additives. If we are using any additive, we have to understand that how the chemistry is changing within this first 24 hours. And formation of more order structure during the earliest hydration will lead to the more durable structure. If we are able to make a more order structure, we can increase the durability. So overall, I would like to say the durability of concrete in sieve environment can be enhanced by modifying the microstructure of cementitious material using during the earliest hydration. At the end, I would like to acknowledge Dr. LP Singh, who is my mentor with this throughout journey and a long journey, and DG NCCBM, all my seniors, juniors, and the friends. Thank you so much. Thanks a lot.
Thank you very much. Thank you so much. Now I'd like to call Vipina Taivalapi and or Piyush Shansali from IIT Madras to speak about the utilization of low-grade limestone for producing calcium sulfoaluminate-Belite cement, please. Thank you.
Good afternoon, everyone. My name is Vipina. I am a PhD student working with Dr. Piyush Shansali at IIT Madras. So since the past 2 days, we have been listening to a lot of talks on the technologies to reduce carbon footprint of cement production. And one approach includes obviously using the alternative low CO2 binders, and calcium sulfoaluminate-Belite cement or the CSAB cement is one such alternative low carbon dioxide binder. And those of you attended yesterday's low carbon cement session, there was a successful production by Ultratech Cement on of the CSAB cement. And one major takeaway from that presentation was, can we use low-grade limestone for the production of the CSAB cement? To answer this question, let's look at my presentation on evaluating the suitability of low-grade limestone to produce the CSAB cement. This is the overview of my presentation. So I'll be discussing few results on the laboratory scale production of CSAB cement using low-grade limestone, few results and discussion, and moving to the conclusion. So the carbon dioxide reduction, emission reduction associated with the CSAB cement is mainly attributed to its difference in phase composition compared to the Portland cement. So the main phase here is the yeelamite, which has reduced raw material CO2 footprint, and apart from this, it requires lesser amount of limestone, lower kiln temperature, and lower grinding energy, and we add comparatively higher amount of sulfate, that is calcium sulfate, to the clinker, which reduces the clinker content, and overall all these factors contribute to a significant reduction in the carbon dioxide emission. And it has got interesting properties such as it is fast setting, it has got a good early age strength, and it helps in shrinkage compensation. It has also good resistance against chemical attack. So all these properties can be harnessed for various special application. However, the commercial production of the cement is very, limited to very few countries. Like China has been using the cement for various decades. But however, other than that, US and few countries in Europe are only commercially producing the cement. The major challenge regarding to the commercial production and the wider acceptance include obviously the lack of standard, and other than this, the long-term performance of the cement as a standalone cement is also being researched, and another main factor is the high manufacturing cost. So if you look at the raw materials which is used for its production, it is limestone, bauxite, and calcium sulfate. And if you look at the major oxide composition, it has got reduced calcium oxide and higher alumina demand in the raw materials. The higher alumina demand will lead to the utilization or relying on bauxite as the major alumina source, which will obviously increase the cost of the manufacture. But however, because of its different oxide composition, it has got good adaptability to use alternative raw materials for its production. The challenges in adopting alternative raw materials is, one is that ensuring the availability for a large-scale production. And another major thing is the spatial and temporal variation in the chemical composition, which will affect the chemical compatibility for producing the cement in a larger scale across the country. If you look at the Indian scenario, red mud could be a potential alternative for alumina, which could partially or completely replace the bauxite, because we have got great amount of red mud being generated annually, and globally also, if you see, the red mud generation is quite high, but it comes with higher pH and iron content, which has to be looked into how it is going to affect the cement properties. And another material is low-grade limestone. I know it's a broad term when I call it low-grade limestone, but because it can come with a lot of impurities, but in general, low-grade limestone means the limestone which is being rejected from cement plants, which is not suitable for the Portland cement production. So especially the limestone with clay and siliceous impurities, it could be a potential candidate for producing CSA cement production because it has got lower calcium oxide and higher alumina demand in the system. So we have collected cement grade limestone and two types of low grade limestone from Ariyalur district in Tamil Nadu, and we formulated along with bauxite and calcium sulfate, we formulated different raw mixes for producing CSA cement with various levels of incorporation of these two types of limestone. So all these binders are supposed to give the similar target waste composition. And how did we produce the cement in the laboratory? So the first step, as I mentioned, it is the proportioning of the raw materials. We relied on Bog equations initially for the target phase composition. We proportioned the raw mix, and we went with wet mixing. Further, these raw mix is hand rolled into small pellets, and it is kept in the high temperature furnace, and it has been heated to up to 1300 degrees Celsius, and with a retention time of 1 hour. Once the temperature is reached, this is taken out and cooled under fast air cooling, and it has been ground to required fineness using a planetary ball mill. So if we look at the mineralogical composition of these clinkers which is formed, we can see that using the low-grade limestone L1, we could go up to 25% incorporation in the raw mix without compromising much in the clinker mineralogy. But with L2, which has got much lesser amount of calcium oxide and higher amount of impurities, you can see that we could go up to 10% successfully, even at 15%, but more than 15%, it resulted in the formation of a secondary phase which is called galenite, that is C2AS, which is less hydraulically reactive. And another main thing is that we relied on Bog equation initially, and we noticed that it is not very reliable, of course, and because it doesn't consider the secondary phase formation and the impurity incorporation in the clinker phases. the clinker phase obtained from Bog equations was much different from the one which obtained in the quantitative XRD. So we also relied on Faxage modeling software to predict the clinker phases. So when we characterized the clinkers which obtained, we could see that even with the incorporation of low-grade limestone, we were able to get similar performance in the early age hydration kinetics as well as the early age strength development. If you compare it with OPC, we were able to develop very good strength even in the one day itself. And another main issue was related to the formation of gahelnite, which, as I said, it not very reactive in the early age, which could compromise the early age strength. So we wanted to look at how to control the formation of gahelnite in the system, and we looked at previous studies, and we found out that there were suggestions on controlling the gahelnite formation based on the alumina-silica ratio. So if you see here, it was suggested to go with alumina to silica ratio of more than 4.5 to have the gahelnite under control. But in our system, if you see, it has got a lot of belite also in the system. So we had very low alumina to silica ratio. In there, we couldn't find a correlation between the gahelnite and the alumina to silica ratio. But so we tried to come up with another factor which we called as modified lime saturation factor. So when we plotted the lime saturation factor against the gahelnite formation, we found out that if the modified lime saturation factor, if we can keep it more than 95%, we can control the gahelnite under 10%. So with this, we could demonstrate how to utilize the low-grade limestone to produce the high Elamite CSA-based systems and how to control the gahelnite formation. Yeah. On another note, IIT Madras is organizing a 4th international workshop on technologies of low carbon.
You have no time for this.
So I would like to invite all of you to attend the workshop, and especially the young researchers are encouraged to participate in the Young Researchers Symposium for the Professor Surendra P. Shah Award. Thank you for listening.
Thank you. Very impressive presentation. Thank you so much. And last but not least, I'd like to invite Sanjit Kumar Mishra or Divya Warmer or Bibi Das or Rajasekaran C or Salim Barbhuiya, and we are choosing you. Thank you so much. Thank you, Salim.
Good afternoon, one and all present here. So I am Sanjit Mishra, researcher scholar from IIT-Delhi, working under the guidance of Dr. B.V. Das sir. So today I am presenting our work synergistic effect of fiber reinforcement and admixture dosage and hydration kinetics, rheology, microstructure properties of blended cementitious mortar. Let's go. This is the flow of the presentation. So as we know, construction industries produces substantial carbon emission, and the production of cement alone contributes 8% of the global CO2 emission. So if you look at the year-wise emission, increment in the emission of CO2 production, so in 1990 to 2021, increment was like 5% at global scale. And in India, it is the 7-time increment. So various techniques are being used to reduce this carbon emissions. One of them is the replacement of cement. So why replacement is crucial? Due to the massive carbon footprint, high energy consumption, and need for the innovative materials. So what is the strategy? We can use the alternative binding materials and supplementary cementitious materials such as natural pozzolan, GGBS, fly ash, calcined clay, and silica fume, etc. So when you are talking about supplementary cementitious materials, then oxide composition is very important. So here oxide composition are presented in the form of three major oxides: calcium, silica, and alumina. So here we can see each material occupies a region that represents a unique chemical composition. In some overlapping can be seen, that is due to the similar oxide distribution. So when you are using like supplementary cementitious materials, we are getting some additional pozzolanic reaction that contributes to the densify the microstructure and increment in the strength. So when you are using silica, we are getting additional CSS. When you are using alumina like calcined clay, we are getting CAH, and from GGBS we can get CSS. So objective is to assess the impact of supplementary cementitious material, admixture dosage, and fiber addition on the flow properties, yield stress, and setting time. Next is to determine the compressive and flexural strength development over time. And the last is to evaluate the microstructural characteristics and development of hydration products in cementitious matrices. So these are the material used. So in cementitious material, OPC, fly ash, GGBS, and silica fume are used, and other admixtures are used. So this is the oxide compositions, and here you can see like in silica fume, the fineness is very around 22,000, whereas in other OPC, fly ash, and GGBS, it is in the range of 300. So that increase the reactivity, fly ash increase the reactivity. Here is the particle size distribution of the various material used. So here you can see silica fume has the very less particle size as compared to the fly ash. These are the experimental design. Mix M1 is the control mix where there is no replacement. Other mixes M2 to M10 that are ternary mixes, and this M11, 12 and M13 are quaternary mixes. These mixes are actually varied depending on the doses of the admixtures and fiber. So this is the experimental methodology adopted. Various tests were conducted as per the Indian and ASTM standards. So coming to result and discussion, first is the flow value versus time interval. So this flow value is conducted at different time interval, where we can see by increasing the admixture doses, flow value is increased. And when we are using fly ash, then also flow value is increased. So here one observation is that when we added viscosity modifying admixtures, so flow value is drastically reduced. So we can see one benchmark is set here, that is 135 mm flow value. So here we can see all the viscosity modifying admixtures here below are below 135 mm. That is due to the viscosity modifying admixtures. So next is the slump and deformation. So in slump and deformation, here we can see mix M3, that doesn't have any fiber content, has the maximum slump and deformation. But when we are adding fiber in this, so that is actually mix M9. So slump is reduced by 33% and deformation is reduced by 71%. Next is time interval, like setting time. So here we can see quaternary and ternary mixes has comparatively less setting time as compared to the control mix. Next is the yield stress. Here we can see control mix has the maximum yield stress, and while we are using supplementary cementitious materials, so yield stress is reduced. And here we can see by adding fiber, yield stress is increased by 30%. So next is the mechanical properties. Here compressive strength in OPC control mix, compressive strength was maximum in early days at 3, 7 and 28 days. But here we can see when we are reaching towards the 56 days, so this compressive strength is comparable to the OPC. Similar observation was found in flexural strength study also. At 56 days, though flexural strength of the mix M9 that has actually fiber content is almost equal to the control mix. It's ultrasonic pulse velocity test. So OPC has the maximum pulse velocity. Coming to the scanning electron microscope image, here we can see that is at 28 days. Here we can see control mix has the more CSS formation and dense structure. However, this M9 mix has some unreacted fly ash we can see, and presence of portlandite is seen. And mix M11, that is quaternary mix actually, it has more amount of unreacted fly ash and pores. Coming to the Fourier transform infrared spectroscopy, so here we can see wave number ranges. Various peaks are seen at the various wave number ranges. So one major peak is near 1000 of wave number range. That is due to the SiO-Si bond. That is mainly comes from the CHS formation. That is actually broad in the case of mix M9. Coming to the TG analysis, here we can see the three range of temperature. One is 50 to 300, other is 400 to 500, and next 600 to 800. So here the quantification, here we can see the bond water percentage continuously increasing as we are moving from 3 to 56 days. That is due to the continuous hydration. Next we can observe here CH percentage is continuously reducing after 7 days. That is due to the consumption of CH to the formation of additional secondary hydration reactions. So here one correlation is established between CSI ratio, compressive strength and bound water. So we can see the lesser is the CSI ratio and maximum is the compressive strength. And the bound water case also, maximum is the bound water, maximum compressive strength is observed. So here one cost estimation analysis is seen. At 56 days, we can see cost is reduced drastically, like 6.49%, but at 28 days, cost was little higher. So flow value was increased due to the inclusion of fly ash, and it reduced the fiber content, and incorporating SCM, it's in the setting time is reduced. Yield stress is increased due to the inclusion of fiber content, and compressive strength at early days was less in ternary and quaternary mixes, but at 56 days it was comparable. So here we can see at the 28th days, some unreacted fly ash pores and calcium hydroxide was seen in the same images, and continuous hydration of. Okay. Thank you.
Thank you, Sanjit, and sorry to be so strict on the timing. Thank you to Shashank, thank you to the 7 brilliant presenters. Now we've got 5 minutes for question and answers. You have been the first one to shoot.
I have 2 questions, one for presentation 2, that is the accelerated carbonation of SCM. So, Mr. Shiv, Sai. Okay, as you know, the polymorphs of the calcium carbonate like aragonite and butterite, these are kind of metastable material. So could you please tell us what is the conditions of the carbonation, accelerated carbonation you have maintained in your experiments, like what are the pressures, what is the time, what is the temperature, so that you can restrict those polymorphs in your SCM?
Actually, what we have done is we have maintained around between 5 to 10%, maximum was 10% for all these adopted SCMs. And what we have observed through this phase quantification was, there was a major amount of calcite followed by wetterite. However, aragonite was not there. And nevertheless, aragonite doesn't actually participate in the chemical reactions. So more or less it was calcite followed by wetterite phases.
No, what is the percent? Percent means you are carbonating by introducing the carbon dioxide gas.
Yes,
right?
of course.
So what is the percentage in the gas mixer or what?
No, that was from the carbonation chamber. It was maintained at around 10%.
Okay, the entire environment.
Yes, entire environment. That was a dry kind of curing that we have adopted.
You said 2 questions, not 10. Okay.
Yeah, and
Thank
the
you.
second question is for paper 4, that is the alkali-activated fly ash.
May the speakers, the 7 presenters, come please here to answer. Can all the answers, these 7 presenters come here? Thank you.
I must say, sir, this is an excellent presentation, how you have shown the amorphous silica getting reacted with the alkali. Just I would like to understand what is the role of sodium silicate in it, as you are using sodium hydroxide as a activator. So in the fly ash, it is already reacting with the amorphous silica and it is forming sodium silicate in the reaction media. So why you are adding sodium silicate externally?
Sodium silicate is used as an external source of silica. It is the cheapest source of silica you can find, water glass, right? So we need to bring in the additional silica because fly ash by itself doesn't have enough silica in it. So the products that are formed are determined by the alumina that is present in the fly ash, and then to bring the ratio, adjust the ratio, the required amount of silica, we bring it from an external source like sodium silicate. That's the role of sodium silicate.
Understood. Thank you.
Another question? Yes, we've got one. Here.
My question is for this your nanosilica presentation. I think we have seen that it has been mentioned in the presentation that nanosilica has formed this your silicic acid. So now question is that how it has been confirmed that it has been converted to silicic acid so that it captures this your calcium ion, again it has formed this your CCH.
Can you please repeat once more that what's the question?
In the presentation you have shown that nanosilica form again CSH. So my question is that that from nanosilica to silicic acid in that condition, chemical environment, how you have confirmed that silicic acid has been formed. So that again it has gone to form the CSI gel formation. How you have confirmed that silicic acid has been formed there?
No. We didn't confirm it. Actually, we have done the ICP analysis where we have monitored the calcium ion concentration as well as the silicate ion concentration. And we have found it out that how the calcium ion concentration is changing with the time. I cannot show that graph it over here, but basically that on that basis we have observed that this silica is able to react with the calcium and is forming the additional CSH, because with the nanosilica we have found out a sudden drop in calcium ion as compared to the control samples. Although I'm unable to show that graph right now over here, but with this ICP analysis and monitoring the calcium and silicase analysis, we have confirmed that additional CSS is forming.
Thank you. Last question.
Yeah, I have a question for Bipina, that is utilization of low-grade limestone for producing calcium sulfoaluminate-Belite cement. Of course, your idea is very good that for manufacturing of calcium sulfoaluminate cement, bauxite is very costlier, so we have to look for a better solution, right? So you have given a very good solution that red mud can replace bauxite. But whether you have done this experiment, because if you are talking about the phases compositions of red mud and bauxite, so bauxite is in the form of alumina, if you're talking about it is in the form of gibbsite, right? And for red mud, it is mullite formed at the high temperature. So as for the reactive pattern is concerned, how we can compare this, and also during our analysis result, and as far the strength is concerned and the durability aspects are concerned, how you can correlate it?
So we have started the preliminary synthesis in the laboratory. Yeah. So what we are seeing is that irrespective of in what mineral form the alumina is in the bauxite, after the clinkering, everything gets converted to the phases we want in the clinker. So whether it is in mullite form or a gibbsite form, it is not affecting the clinker phases. Rather than that, the major concern is the high alkalinity and high amount of iron in the red mud, which is going to affect the clinkering reactions as well as the properties of the cement, which are under investigation now.
Okay, thank you. Thank you very much. So now I would like to conclude this. Very nice presentations from all the presenters. And I think it has done justice to the cement chemistry sessions. Of course, as usual, like always, I learned something from the keynote speaker today, who has given a new thing like the use of this water repellent properties for this new cement. Second, we have also discussed about this GGBS-derived mix by using this accelerated carbon curing. The third paper was also very good by this B.L. Subramaniam, that is assessment of utilization of fly ash through this alkali-activated cement. Of course, it can prove, as per the CO2 emissions are concerned, it can prove a better solutions of the different fly ash that we are using. The fourth paper was also very good, that is a characterization of high volume M3 halide polymorph by Rajesh Kumar. Nanosilica particles, what is what is the impact on the durability aspects and also the early hydration properties using this nanosilica. That is I think a very nice paper too. Of course, this utilization of low-grade limestone has also proved to be a path, because we are also doing some experiment for this red mud. So we can use this subject very well. Synergetic effect of fiber reinforcement and admixture, doses of hydration, rheology and microstructure. I think this was also a very nice paper. So thanks to everyone. And now I will request chairman, if I have missed something, then he can take it.
I don't think you missed anything. I think the keynote was great against all odds. That was really great, thank you. And the 7th presentation were very, very interesting too. I learned a lot, so I would like to personally thank all of you. I think it was very, very new, very well done. So big, big congrats to all of you. Thank you.
I request our chairman of the session to present keynote speaker, Professor Shashank Bishnoi, with a moment of appreciation, with a token of appreciation. My apologies. I request our chairman and co-chairman to felicitate all the presenters with participation certificates. I'll call the names. Mr. Shiv Trivedi, Mr. Himanshu Guleria, Professor KVL Subramanyam, Mr. Rajesh Kumar, Dr. Usha Sharma, Ms. Bipina, Mr. Sanjay Kumar Mishra. Congratulations to all the presenters. I request Mr. Brijesh Singh to honor our chairman and co-chairman with mementos. With this, I conclude this technical session. Thank you for your presence, patience, and participation.